So if this is the first time you see me talking, I have a little advice. So I tend to talk quite fast, so I hope you have your coffee ready. It's going to be all right. Cool. So I'm actually really excited to present you to all of you. So this is the combination of a lot of work. And I want to start to introduce actually why I wanted to do this. So when I started to use Python back in the day, I came from the compile world, so I did C, C++, and Fortran. And in those worlds, debugging is maybe not the best, but it's not horrible, right? A lot of people have put a lot of effort to ensure that, at least you can debug these things, right? And one of the things that I find really cool was the possibility to have some application running, and then you have a debugger. In this case, it will be like GDB. And then you can attach to the application that is running without stopping it. You check a bunch of things because maybe it's misbehaving and it's doing some weird stuff. And then you kind of understand a bit, and then you keep it running. And so Python has a debugger. It's called PDB. You may like it or not, but it's what we have. I mean, there are others, but the problem is that when I try to do the same thing with PDB, well, there is nothing like this. And when I ask around, why PDB doesn't support this, the answer is well, Python doesn't work like this. So 10 years after, now I'm here to tell you, yeah, it actually works like this. All right, so what I'm going to tell you here is basically the idea. And this is a trend that I think I started some time ago because I think Python, the shares a much better debugging experience. And I want to start doing some comparisons with medicine because medicine has changed quite a lot. It's quite wild, if you know how MRI machines work. MRI machines in medicine was quite a revolution. They were introduced in 1977, and when you start analyzing, I'm a physicist, right? So I had to study in my degree, how these things work, and it's quite wild when you realize what it is, right? Because people know that it's magnetic fields, but magnetic fields are just light. So technically, these things are using light to understand how you're working, right? How your cells are behaving, how are your organs, and get a precise map of what is wrong with you without actually even cutting you open, right? That is fantastic. This thing actually produces, it's quite wild that we are able to produce these things. This produces magnetic fields that are 60,000 the magnetic field of the Earth. We've been able as humankind to produce 60,000 times the magnetic field of a planet, right? And then we use this to charge you a bunch of money and to try to find what is wrong with you. So before MRIs, medicine was kind of wild, right? I remember that it was quite common in the medieval times to if you have a headache, I suppose it was time to open your head, or if you were have a depression or something, then they will put you in cold water or something, right? So, but now, we went from the medieval times to the MRI machine. So how is the Python debugging experience looking? Is the MRI machine? Well, a Python experience looks more like this, right? So as you can see here, this is an RP called 2 senior engineers and the manager debugging a live application. You can identify the manager by the person with the book in the head because it looks like it's helping, but it's not. So I have actually something to say. So when I have this image, I actually did the responsible check, and I checked with my manager. I was like, as a manager, how offensive is this? And he's like, well, it's kind of funny. So we actually look at the story of this piece. It's by Bosco, and apparently this is precisely what the guy wanted to say. The person on the right represents the church or whatever, and what he wanted to say is they try to help, but they don't know why, and the book in the head is kind of representative. So full circle. All right, so debugging in Python is kind of bad, because, and it's kind of weird, right? Think about it, to debug in Python in this sense, if you have an application in production and it's making money and whatnot, and these things these days take a bunch of time to start. Let's imagine you have some Redis cache and some database and a bunch of things, and then you need to bring those up again and ensure that all your application starts. So this takes a while, right? And if your application is doing some weird stuff, especially if it's a distributed system, that's a problem. You need to restart your application just to know what the hell is going on. Going back to the medicine metaphors, this will be the same as telling okay, if you have a patient that is sick, well, the solution probably is just kill the patient, resurrect it in the in the table, and just hope that it gets sick in the same way, so you can actually inspect what is going with it. So you laugh because it sounds stupid, but it's because it's stupid. And this is how we are debugging Python applications these days, right? You just restart it and hope for the best, right? Maybe add some print statements. So hopefully you will see that after this talk, it will change massively how you can debug Python applications with 3.14, because the whole thing is going to change, and it's not only just about PDB minus P. It's this is going to open a new thing, a new field of tools that can do very cool things with the Python interpreter. And I'm going to show you some ideas, things that you can implement on your own places. All right. So let's go into business. So what is the problem? What is the problem? So let's imagine you have the Python interpreter over there, right? Okay. So let's kill the Python interpreter and let's see the problem. Let's see what is going wrong, right? So right now, the problem of like trying to analyze this thing is that if you bring it up, or instead of killing it, and then you want to attach from a different process, you can do many different things. One of the things that you can try to do is to use a native debugger. So instead of like using PDB, let's say, well, why we cannot just use GDB, like the real one, the C one. So that's why I'm using now this code. This code represents like compiled programs, right? So the way debuggers normally work is that you will use a system call in Linux, at least. macOS and Windows have similar things. So we'll use a system call called ptrace. And when you call ptrace, the kernel will basically stop the other process, and you will be in an attached state. So like one process now can control the other. And then when you need to wait for the other process to stop, so the process will be asleep, and then the process will just freeze, right? And at that point, you are technically attached to it. And then using the ptrace system call and changing just what you pass into the call, you can actually like inspect a bunch of things. For instance, something that you can do is called this thing called ptrace get registers. And with this, you can get just a bunch of binary back. And this binary can be anything. For instance, in this case, I'm asking for all the registers that the project has. And knowing all the registers, I know all the state of the CPU at the time I'm attaching. Among other things, I can know like what function is this running, the value of the local variables that are in register, and etc. So we are in the low-level territory, but like at least you can get a hint on where the information is coming from. So one thing that you could do is, like, for instance, you could read memory. So there is this other like thing that you can pass, it's called ptrace pick test, and this allows you to read arbitrary memory. For instance, here I'm just reading the value of the instruction pointer, and this way I can just know, like, okay, what is the function that is being executed right now, and I get like some address back. And like the name of the function is a more difficult thing to get, but like at least you can know more or less where the program is going. So something that you can do as well is you can modify memory. So this is how debuggers change the function that is running or change locals and things like that. The system call is called ptrace poke test, and that allows you to just modify the memory, right? In this case, for instance, I'm modifying the instruction pointer to say, well, instead of running that function, now you run this other function. You need to change all the registers, right? You need to change the stack pointer and probably save all the registers that you have, so when you go back to the original function, it doesn't crash. And then you can say, well, where are we going to do this? Well, because if you do this with Python, like for instance, you just say, okay, let's call a function in the process that I'm debugging because I want to just maybe print a value or whatever. So you can like maybe find what your function is, you put it in the instruction pointer, you pass 42 to the function because you're calling it with 42, you put that in the RDI register, and then you call it. So what happens, normally you call ptrace continue just so it doesn't sleep, and the whole thing explodes. The whole thing explodes because it turns out that you cannot just do this arbitrarily, right? Like there is this thing called unsafe and whatnot, and the reason is because programs are not ready to just be like arbitrarily modified and then just suddenly you go into a different function. You can think about why this is the case. For instance, one problem is malloc. So malloc, the allocator in C, and the C runtime, malloc has a lock. Which means that if your application happens to be already allocating memory and then you do all this business and then you call malloc, you deadlock because you are trying to acquire the same lock that has been acquired above you, right? And this is just one example. You can imagine how this can go really, really, really wrong, right? Like for instance, in Python, we have tons of lock. Actually, we have a big one. so if you try to mess with the big one, then you probably will deadlock, right? So this is one big problem. The problem is that there is a lot of tools that say, well, we don't have PDB minus P or something, but we have GDB kind of thing. So maybe we can do some fancy low-level things and attach to it. But the problem is that like Python is fundamentally unsynchronized with this mechanism, right? Like the problem is that you cannot just hope for not being under malloc, right? And there is like malloc, but there is all sorts of different things. If you actually go to like the C runtime and the standard or the POSIX standard, and then you check all the functions that are actually signal safe, which is the ones that you can actually call without like being afraid that you're going to blow up just because you call them, they are very, very little. Actually, it's not very fun to just use all those functions, right? And most of the time, what these debuggers that using GDB try to do is to just spawn a thread and then maybe like try to connect to it from a remote server, right? For instance, if you use VS Code, the debug debugger tries to do this with the GDB or LLDB, depending if you are in Linux or Mac OS, and I don't know what the hell they use in Windows because we don't care. But like, but it's really bad, and the reason is because like if you do it in your laptop, it's maybe okay to destroy all your work, but if you do it in production, it's kind of not really okay, right? So this is one of the problems, right? Like where we cannot use. And what I want you to remember about this, because you say, okay, Pablo, there is a bunch of registers and whatnot, but like, what is the point? Well, the point is that you have the Python interpreter, and the Python interpreter is unsynchronized with all these debuggers. Like it doesn't know there's going to be a debug, and therefore it doesn't know when it's safe to attach, right? So actually, for instance, in memory, which is a debugger memory profile I do, we are allowed to attach to process using this trick. And here you can see how we kind of try to avoid our best thing. So what we do is that we put breakpoints on all the functions that we know they are not safe to go into. So for instance, we try to break in malloc, all the allocators. The list is like probably 80 functions more. So what we do is that we try to put breakpoints with the debugger in all these functions to ensure that only when we hit one of these breakpoints, maybe it's safe to attach. But this is horrible. Like this is horrible because you can if you see this list, you can start to be really afraid, because like what happens if you miss one of these, right? Like what happens if like turns out that you move to a different system when like you forget one of the allocator calls and then it goes into it, you try to touch and it blows up, right? So that's kind of bad. And like then the kind of thing that you will do if you do this kind of approach is that you will wait for one of these breakpoints to hit, and then you will open an entire set of object that has like some constructor. So you will run arbitrary code that sets as your debugger, and then your debugger will say, hey, I'm ready, you can attach now, and then you will attach. Which is all of this is like horrible. It's just disgusting. So now like the idea is that we need some way for the interpreter to tell us like, okay, now it's safe to attach, right? And this is what the whole thing that we are going to present is going to be about. So again, so you have these two processes. So we cannot treat these two processes as arbitrary process because one idea is that you could say, well, what happens if we kind of like send bytecode from one process to the other? Like, well, we cannot do the same thing as the registers that GDB was doing, but just with Python. The problem is that like you cannot just send like bytecode from one process to the other and just hope for like driving the process, because like that is not going to scale, and it's very hard to just control the low-level operations that you need to do. The problem is that these two processes are basically speaking different languages, right? Like one process basically speaks like all the C language, and then all the Python stuff is missing because you don't know like when it's safe to attach and like what functions are safe to attach. But what you want to speak is like bytecode, but like that, the debuggers like GDB and whatnot don't speak bytecode, so we need something else. So basically, it's two different languages, and we want to make them speak the same language, right? All right, cool. So again, let's go. So how we do this? Well, it turns out that one of the functions that a lot of profilers use is this system call called process VM readB. So this system call, among other ones that are similar in macOS and Linux, this process system call allows to read arbitrary memory from a process. So you can go to a different process and have an address and a size, and then you can say, give me a chunk of memory. And then you can read it. It's so cool that you actually don't need to even stop the process. So this is how profilers, like sampling profilers work. It will call this function with a PID and a bunch of size, and it will read from the other process all the functions and all the data to reconstruct what it's doing. So this has been used in the industry for a long time, and people know it is very popular. But then, you know, if you go and read the thing, I was checking, and I was basically remembering this sentence for Inception. That is like, well, if you can actually steal an idea from someone's mind, in this case reading memory, why you cannot plant one there instead? And why I say this? Because the same way there is process being read B, there is process being write B. Nice. And I was like looking at this like, what can I do with this? This sounds much fun, because like, you know, one is reading, but writing, man, that's a different thing, right? Like, that's where the fun starts. So this little system call is going to be all that we need to actually implement all this safe debugging business. So let's see how it works. So we put all of this in PEP 768, which I did together with Ivona and Matt Wodniewski, which are my co-workers at Bloomberg. The PEP is quite complicated because like it not only like says all these things that I'm going to talk about you, but like it goes into like security and like all sorts of different boring things, right? So unless you're a security engineer, in which case I'm very sorry for you. All right, so how it works. Cool. So this is the setup. So we have a Python process on the right, which is running and it's happy and it's doing its thing. And then we have the debugger on the left. And we want the debugger to basically attach to the process on the right. All right, first thing, like it's just like impossible to know when to attach. So we need a way to know when it's safe to attach and how to attach. So we are going into detail on how that is going. All right, so for that, what we did is to implement a new function, which now sits in the sys module called remote exec. And this is because every different debugger is going to do different things, and it's going to require different things and different setups. Maybe one debugger opens a port that you can connect to it. Maybe another debugger just to write to a file. I don't know. So we make it generic. So the function that we're going to implement to allow these debuggers to do this business is a function that is called remote exec. It takes a PID, a script, and it executes the script on the other part, right? It's a way to force a Python interpreter that is running to execute some code that I want. And you set up your stuff, and then you can do whatever you want. All right, how do we implement this? All right, so first the thing, we need to identify a safe point here just to run, because you cannot just run, we cannot just force the Python interpreter to run a script at any point because it will crash, right? This is the business that we discussed previously, right? So we need a safe point, and then we need a way to basically say, execute this script. So to basically to pass the information along. And the process is unmodified, right? So the idea is that you don't want this process to spawn a thread or a socket that you can send some data into, because then you expose yourself to a lot of problems. All right. So how we do this? Well, why a file? Well, that's an interesting question that I will mention at the end, but the idea is that first you obviously need to write the file. So for instance, just to be absolutely clear how this will work, you have a temporary directory with a script, and then you write the string hello world to the string, and then you call remote exec, and the other process is the one that is going to print, not you. All right, so how we do this? Well, we leverage the evaluation loop. So this is going to be our safe point. So in CPython, for instance, you have a function, as you probably know. This is probably going to be the less technical slide in this conference, because we have been looking at JITs and whatnot. So I'm pretty sure if I put some bytecode, you wouldn't be afraid. All right, so in Python, if you have a function, those functions are compiled into bytecode, and the bytecode is executed one after the other. But at some point between those bytecode instructions, there is this thing called the eval breaker that will stop everything, and it will do a bunch of periodic things. So for instance, the eval breaker will check for signals. Like when you send Control-C to the process, that is not executed immediately, because again, the interpreter cannot just execute the Control-C code immediately. It needs to wait until it's safe to do so. These days, the garbage collector also runs in this place, because it turns out that we learned very painfully that you cannot just execute the garbage collector arbitrarily in any point in the process, because fun things will happen, and we are not fun people. So we decided that it's a much better idea to run it here. And there is other things the JIT executors clean here and whatnot. So this is a perfect point, because we already know that this point is fantastic and it's safe. So the idea will be that once the interpreter reaches the eval breaker, it's going to check something. We will discover where the something is in a second. It's going to check something, and if the something is set, basically our debugger wants to execute something, it's going to just go and run it, because at that point it's safe and it's all good. All right, so we call this remote exec to the other process, and then we need to put the something somewhere. All right, so where is the something somewhere? Well, so we are going to have basically an array, which is empty right now. That's the box with the X. So that array lives in the remote process. So all Python interpreters now have this array. And normally it's empty. And our job is going to be, as a debugger, to write to that array. And then once we write the file that we want to execute to that array, the interpreter will run until it hits the eval loop. It will check that the array is not empty, and it will execute it. Very simple. So the problem now, the whole business is going to be how we find that place, because every Python interpreter will have the array in a different place. So we need to be able to find that place in an efficient way, and that is going to be the most complicated part, right? But let's see how we can reach that guy. All right, so the first thing is that we need to find where the Py runtime is. So the Py runtime is a structure in the Python interpreter that contains all the information about the entire interpreter that is running. So not only the interpreter in the set of the sub-interpreters, the entire thing. This is all the state, right? So it's a big C struct that sits somewhere. All right, so the cool thing is that since Python 3.11, I think, we added a secret thing on all the binaries. So if you compile Python, and it will change depending if it's an ELF in Linux or a Mac O in Mac OS or whatever Windows uses. So if you analyze the binary, there is a secret data that we burn in Python since Python 3.11 called _PyRuntime, or if you're in Mac OS, I think it has 2 underscores, because why not? And this contains an offset in the binary where the Py runtime is. So this means that if you count these many bytes from the style of the binary, you will find all the data of that global structure. And you will say, well, that's awesome, that's it, right? Like, we have it. No, because turns out that, like, security is kind of important. So these days, you don't load the Python, when you load the program, you don't load it at the same memory address, because, like, hackers could, get the addresses and understand how your program runs and, like, hack it if the addresses are the same. So normally, the Python interpreter will be loaded at different addresses every single time, except on Windows for some reason, which I don't understand, and I don't want to understand why that is the case, but, like, we also do it just in case they decide not to do it. So the idea is that once you have this number, you still need to know where the Python interpreter was loaded. All right, so we have the number, but we need to add something that will tell us where the Python interpreter was loaded, because this is a relative number, right? This is the amount of bytes that I need to count since the start of the Python program, but I need to know where the Python program is. So to do that, it changes depending on the platform. In Linux, it's relatively easy, because it turns out that you can inspect the proc pseudo-file system and literally ask the kernel for all the memory maps that you have been, that are loaded in the process. So the output is a big list, but basically you will find something like this, in which you have like an absolute virtual address, and then the Python executable. You will have many entries, but like you just want the first one, and that is basically telling you where the Python interpreter was loaded. Reality is a bit harder it's a bit harder just because, like, you can deal with Python or leave Python, depending if you compile it with like a set object or not. But like you still get it. So adding those two numbers, now you know where the Py runtime is in the process. So that's kind of cool. So now we know where that structure is. All right. So now we can call process being read and read the structure from the process. So we know what the structure contains, right? And this is going to be the business. This process drive Gukas Langa crazy when he was doing this, because, like, basically you have a pointer on the debugger, but that pointer is pointing to memory on the other side. So you need to, like, copy the memory until you read it. So you cannot just do a start, because then you blow up, right? Because it's a fake address. Fun times. Anyway, so you copy that memory, and then you know what the process, like the runtime contains, right? So you now know all the big structure in the interpreter. So now we need to find still the box, because the box is not in Py runtime. All right, so now Py runtime has a bunch of fields. The first field is something that we added in Python 3.12 called PyDebug offsets. So PyDebug offset is basically a big struct that contains a bunch of, like, stuff, like contains a bunch of versions just to know what you're doing, but basically it contains information over a bunch of structures in the interpreter and all the different shapes that they have. And this is something that we will use to, when we copy memory from the other process, to interpret that memory, because, like, we are going to copy just a bunch of raw bytes, but we need to know that those raw bytes are a list. And to analyze it as a list, we need to know, like, the offsets of the different fields of the list. And we could use the debug information, but you could strip the debug information out of the binary, and that's not great. So we use these, like, big structural offsets to know, like, okay, these bytes that we copy is a list, and, like, it has this shape, and then we can interpret. So it's like a map, like some kind of map of sorts. So once we copy this thing, now we are able to interpret Python objects now on the debugger. All right, so using this, for instance, like, we modify the list to add a bunch of extra stuff. Like, so this extra stuff will allow us to know where the box is and, like, what is the debugger is, what the debugger fields is. So there is a bunch of fields, but one of them, if you see, is this debugger script path. So the debugger script path is precisely the location of the box. But it's the location of the box, obviously not in absolute terms, because it's just an offset. It's the location of the box relatively to the thread state, because we want a box per thread, just so we can say, you run this, or you run this, or everyone run this, right? So then it means that with this information, we can know where the box is if we know where the thread state is. So the operation is a bit annoying. I will skip it fast, but basically from the runtime, you copy the debug offsets. From the debug offsets, you copy all the runtime. The runtime has a bunch of interpreters, because sub-interpreters now is a thing. So for every interpreter, you need to copy the thread state that tells you how the threads look like. Every interpreter has a collection of threads, so you have a lot of them. And then every thread will have, like, its own structure that contains the thread ID and a bunch of things. So you locate the thread that you want. You need to tell me which one you want. Normally you want the main thread, but you can select a thread that you want. And then you have this particular structure. And then knowing that structure and the field that we just copied, we know where the box is, right? So we will have a structure that looks like this. There is a bunch of garbage inside. This structure is really big. And then once you have the offsets, well, you can just add those offsets there, and voila, there is a field there called the debugger script path that has, like, a big array, and then we just, like, right there. So just to be absolutely clear, like, the offset from the thread state to this place is quite deep. So, like, you still need to copy the entire thing, which is big, and, like, you need to allocate all the memory over that. But conceptually speaking, you're going to have a pointer to the beginning of something, and then you add this offset at the end, and then you just have the location of the box. So you can read the box to know if there is something there, or you can actually write to the box to just force the program to run something. So, and then in ceval.c, so this is the eval breaker, right? In ceval.c, the code is quite simple. Like, let's put a bunch of quotes there, but basically what we do is that we check if you have set a bit that is called debugger pending call, because like reading obviously the box is kind of annoying. So like what you're going to check is like when you write to the box, you need to write the actual script that you want to execute, and then you need to set a bit that says, hey, I have write something. This is also to not raise, because like you could be writing something to the box, but you may be halfway there, and if the process tries to read something, it may see that you have write half a string, and it tries to execute half a string, and fun things will happen, and we don't want that. So like you need to set a bit when you're ready. And you can use this to also not raise with other debuggers. So basically, we check like if the bit is set, and then we check where the path is. We call process being write B, we write it there, and then there's a bunch of like boring stuff. Like for instance, you call the audit system to tell like, hey, someone is going to execute code, so you allow the process to decide if it wants to execute code or not, and you write all the audit system hooks and whatnot. But at the end, we call run any file, which is a CPython call that allows you to run a Python file, and voila, the other guy executes whatever we want. There is a bunch of questions here that I'm not going to detail, because you could say, well, what happens if I raise an exception in the exception code? Right now, as you can see, we just ignore it. We just print it and say, well, some bad thing happened, whoopsie, and then we continue. But you could do whatever. Like you could select not to do that in the future. All right, so that's the whole idea. So you could say, well, it was kind of easy, right? Like conceptually speaking, you just say remote exec, you write to a box, and that's done. But if you remember, like you put all the things that we did here, it's quite annoying, right? So the PEP was difficult, and we suffered quite a lot. But now it's there, annoying. Awesome. So nice, nice, nice. So now let me show you what you can do with this thing. So here, now that we have this function, so I have a program that is running over here. It's happy running there. It's doing a bunch of things. And now in Python 3.14. You can say, in macros you need sudo, and we will go into this in a second, but you can run Python minus m pdb minus p, you pass the PID of this guy, you put your password, and then whoops, wow, it's stopped, and now look at this, I can just run BT, and I can just check what is going on, I can run next, and if I run next enough times, the other guy is moving, but it's only moving when I allow it to move, or I can detach like this, and the guy continues running. Amazing, eh? Awesome, it only took a year of work. All right, all right. Oh, cool. So you will say, well, Pablo, I don't trust you. As Mark Shannon likes to say, this sounds like remote execution as a service. Not great. Can I deactivate this? And the answer is yes, you can. If you are in the non-fun people club, but you can do it, right? Like all the security things and whatnot. So we have a bunch of like increasingly nuclear options to deactivate this. One of them is to set the Python disable remote debug. I really wanted to call it Python no fun mode =1, but like, the Steering Council didn't allow it. Wow. Well, anyway, so you can set this Python disable remote debug to 1, and then the Python interpreter will just refuse to just execute whatever you want, right? It's like, oh. You can also run it, because that will affect all Python programs on the environment. You can also run it with this -x disable remote debug, and then that will only affect your Python interpreter. And you can say, well, but I still don't trust you, because I'm running this like very boring financial institution. I don't like these environment variables. I just don't want it. I just don't want it. Okay, so you can compile Python with this like very non-fun flag like that. You will be boring, really boring. Like people will not invite you to parties and things like that, right? Like, no, we don't want this. But if you are in one of those annoying places, well, you can compile Python yourself. You need to compile Python yourself. But like you can run with this thing, and this thing basically will do is that it will not compile the code in. So there is a bunch of macros, and it will say nothing out, and therefore like there is not even the code there. So like it's not that it's going to be deactivated; it's that the code is not even there. So like you could compile Python without all this funny business. It's just that now you lose debugging and all the fun tools. And increasingly, the Python ecosystem is going to support this more and more. So obviously, you compile this way, a bunch of things won't work. But I don't know. Maybe you're running on like some weird place, and you just want it there, and you don't want anyone to mess with your process. So you could set this up, right? So cool. All right. So as you can see, we didn't just did like PDB minus P, although that was kind of like the objective that we want to give to. So like now you can run PDB minus P as I showed you, but like what we really want to do here is to set some building blocks for everyone to use. So that's why we just didn't add the feature. We had this like sys.remote exec. obviously, like, this is a tool for debuggers, so please don't do this as a way to inter-process communication, use gRPC or something. Don't blame me, okay? I say the words. Anyway, so the idea is that now debuggers, different debuggers and profilers can drop their disgusting things and like just move to this thing. But now you can also do tiny tools, and I want to just show you some examples of the tiny tools that you can do. Because the cool thing about building blocks, and I have learned this since I've been a code developer, is that you may think like, okay, I'm adding this thing over here because it's kind of cool and I think people are going to use it this way. But people are kind of weird and like they grab your thing, like, what happens if I put it this way? And like now it's kind of cool, right? So this is what I want. What I want is that a lot of people start to use this and see cool ways to adopt it. In the standard library, actually in 3.14, we are shipping with a bunch of other things that leverages this, not just PDB-P. There is like a bunch of async.io, introspection things that, you can search in YouTube. It's banana related. If you search in YouTube, you will understand. Anyway, but I want to show you some examples of things that you can implement because you don't need to implement a full debugger to benefit from this, right? All right. So, for example, PDB-P, blah, 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 we see this already. All right. So imagine that you have, like, for instance, like a web server, right? And the web server is like there and it's logging on warning. Right? And then a bunch of weird thing happens, right? Like maybe you see like something is going wrong. So you want more information. So unfortunately, if you're logging on warning, you're logging on warning. That's it. You cannot just not log on warning and log on debug suddenly. But now, with this, you can force the process to change the login level on the fly. And now you can say, well, something's going on. I want you to log on debug. And now the web server logs on debug, and now you can read what the hell is going on. And you will say, well, that's kind of expensive, so when you finish debugging with your thing and just getting your logs, you can make it log on warning yet again. So like you can change the login level on the fly, which is kind of cool. Something that you can do, imagine that you have like a bunch of weird things, so you can implement something on your other process or on the profiler on your little script that forces your process to print a bunch of diagnostics. So not even attached with GDB, maybe you already know. So for instance, in this web server, so all these are real examples. So in this web server, for instance, I'm forcing it to like print all the connections that are alive and all the APs and what is listening, and like all the sockets that they have, and like maybe some warnings if there is a lot. So if there is something going on in my production server, something like that, I can have a system that automatically injects this on the process and forces it to print, so I can put it maybe on the ticket or whatever it is that you're doing to debug this. Another problem is, like, for instance, imagine that you have like a lot of memory in your process. You may say, well, I can attach a memory debugger, right? You actually have one. Yes, but like the problem with memory profilers is that they need to see you allocating the memory. So if you have a process that is already using too much memory, well, bad luck, because the profiler has not seen anything. But something that you can do is to use this thing to force the garbage collector to print all the objects that are alive in the process and categorize it by type. So for instance, here, I'm forcing it to print all the different types of objects and like which ones are like they have more instances alive. This is not by size, it's just by number, but you can like immediately get the size by calling sys.getSizeOf. You can literally do that and just print the biggest objects. For instance, I'm printing here all the objects that are bigger than 10 megabytes, and you can see that there is a big JSON there, and like there is a transaction object that probably some weird thing is going on, or some like image over there. So you can literally go and inspect the other guy without like affecting it, right? And this is really great because like if you do this with a native debugger like GDB, interpreting all this data is normally impossible because you need to print that dictionary. You need to print the dictionary. Like you need to run code, and normally like you don't want to run code from a native debugger because like it's very, very, very dangerous. But here, you know that when you are printing all these objects and you're executing this script, it's always as a safe place. So like printing this data is always possible. Something that you can also do is like print all the modules that are loaded. So this is a very good example and where they are coming from, because sometimes, like this has, these are all obscure bugs that you can fix with this, but like this has helped me quite a lot because like some people, change the modules on the fly and they say they're running some code, but like you go there and they're running a different version of the mode. So you can like literally print all the modules and maybe the versions, which is not here, but like you could print the versions so you know immediately when an application is running. Or you can imagine like if you have like, a big company or whatever and you're running a lot of Pythons, like you can sample all the Pythons that are running, and then you can ask what models they are running, and then you know what versions of the libraries your users are using, right? So you know like, oh, I need to deprecate a library. I know that this guy, and this guy is using the library. Or you can, like, for instance, force a garbage collection run, right? For instance, if you have the suspicion that like your super ML whatever mega tangle tree of objects is running like out of memory because it has a lot of cycles. Normally that's a bug in your code, by the way. No, don't blame the garbage collector. So you can run this and force a garbage collector run and maybe try to decrease a bit the memory pressure on that. Well, anyway, so these are just some examples, right? So the conclusion is like, I like to think that this is kind of like the Python MRI moment, because it's kind of like the technology that unblocks inspection. So now, obviously, the MRI moment doesn't immediately tell you what is wrong with you. Like, it needs a doctor that actually sees the image and like interprets the image and say, well, okay, this means this and that. So this is not going to tell you exactly what is wrong with your applications, but it's going to help you a lot. Not only that, like now it's allowing the MRI moment to actually change a bit your body, which you could argue that maybe it's not a great idea, but like, you know, maybe you know what you're doing is cool. But I'm very excited because I think like with this, you can actually start building like much cooler tiny programs and big debuggers, right? So people like the people that are maintaining the debugger in VS Code can now drop their like mega code that injects like crazy things, and now it allows you to like attach to the process. Or for instance, myself that I run like this memory profiler memory, I can remove all this disgusting code and like just use this thing instead on Python 3.14, right? Like before we still need the disgusting code, but hopefully 3.14 will be all news very soon. But yeah, like I'm really excited to see this, and particularly I'm really excited to see what you all do with this and with the ideas that you come up, because we like Python right now is one of the, if not the most important language in the world, at least like the most used, and I think like we deserve modern care because we've been opening like heads at before time. So it's time for the MRI moment, and it's time for all of us to have a good debugging experience. So with this, I hope that you have enjoyed this, and it's time for questions.
All right, thank you so much. Are there any questions? If yes, can you please come to the, yeah.
Hello. Thanks for that interesting talk, very informative. I was wondering, can you attach multiple things to a Python process at one time?
So yes, but so you need to do one every time, right? So you can force a lot of scripts to run. You can even run this in a loop, but like right. not two at the same time, right? You cannot race.
Okay, because I was wondering, is it possible to, I don't know, decorate a Python process with, I don't know, attach.
Decorate a Python process?
Yeah, like you were now attaching Sentry to my Python process, and it will just, attach Sentry to it and upload all the stats.
All right. So in theory, yes. Like I don't know what attach Sentry is in this context, but that sounds like an interesting thing. But like you can do it because this is generic, right? Like the thing allows you to only run code. So for instance, let's say you have 5 things, and one of them attaches to port 1, 2, 3, 4, and the other 1, 2, 3, 5, and the other 1, 2, 3, 6. Right. Like this process doesn't know about ports or anything. You just say, well, start a server on this port, and then you attach, and then you run it again and say, start a server on that port, and then you attach. So you can attach all that you want because attaching here is like just a way of running code, but like as you can see, it's anything. So if you can run any code and set up something, then it's okay. One important thing, of course, is that you are executing things on the process, which means that you cannot import a module that the process doesn't have. No. I mean, sorry, you can import a module, but if it's not installed, I mean, you could sell out to PIP, maybe, maybe whoopsie. But like, like if you don't mind doing that, maybe you can do it. But like, if you don't have Sentry installed, for instance, you cannot do it, right? But if you have Sentry installed on your Docker container or whatever it is, then you can attach as many things.
You cannot run arbitrary sidecars.
Yeah. It's just that you cannot like attach at the same time, right? But you can, for instance, attach 2 debuggers in the sense that you can set, for instance, again, a server for a debugger and a server for another debugger, and that's done, and then both debuggers attach, and you need to figure out how to not race between them, because like the debuggers normally use sys monitoring or sys.trace or profile, so you can just have one of those, but that's up to you and your debuggers.
Okay, thanks.
Are you so low? Are we expecting this to be forward compatible because of the pinning of the location for under Py runtime? So like if I want to attach to a 3.15 process using remote exec from 3.14, is that expected to probably continue to work and work going forward, or is the magic you're doing specific to the Python version? So
that's a very good question. So the protocol is technically forward compatible, right? In the sense that the debug offset thing that I mentioned contains enough information to know where the box is at any point. Right now, in 3.14, if you use sysremote exec, that is one-to-one compatible. So like you need 3.14 to 3.14, 3.15 to 3.15. The reason is because like we don't want users to be confused that you can attach to all versions of Python from new versions of Python. So like for instance, imagine that Ubuntu ships with 3.14, but they have a 3.13 thing, or well, 3.15, 3.14, right? And then it doesn't work. So we want to just do the restricted version first and then open it. But if you re-implement this is a protocol, right? So you can reinterpret this on Rust. And then you can attach to any process from your Rust process, right? Because the debug object contains enough information about like the running thing. So it has the version, it has like if it's threaded or not, it has like the shapes of all these structures and more. Like it actually contains enough to interpret like even Python objects. So you can just get a bunch of memory and say, okay, this is a dictionary and it has this shape.
Thanks.
So just the kind of current status quo 3.13 earlier is for things like VS Code is to have like debug actually in your code, and that sets up the port and you're doing the things across there. I take it this is effectively a deprecates the need for that. You could effectively do all the same things that debug is doing, but you're doing it through a Python kernel provided interface. That's the intention?
Yeah. I mean, even the debug like for instance, the debug author was in the PEP discussion, and like one of the things that they were saying is that they were quite happy because they can throw all this like nonsense. Because like the way it works is that you need this shared object injected into the process and then executing the code. But like to inject the shared object in the process and run Python code, you want to run it with the universal API, right? For Windows, for instance, and all the stuff, right? So it was a very painful experience because you are very limited to what you can run, and now you need also the debugger to work, and like sometimes it doesn't work. So the idea is not to replace debug is to allow debug to do this thing in a safer way. So you could use debug in production, that's the idea. Okay. But yes, you could implement your own debug now much cheaper.
Sure, but you are still going to need, it's only at the process level you don't have like connection to arbitrary other machine or running the debugger on a separate machine.
Right,
you have to have the PID.
Exactly, yes.
Okay. Right, thank you.
So one question I have is how this works with sub-interpreters. I'm guessing it sort of,
it doesn't. No, I mean, right now it doesn't because like so sub-interpreters that right now doesn't have a established concept of a thread. Like, I mean, the concept is there because a sub-interpreter runs a bunch of threads. So technically, targeting a thread really means targeting a thread in a sub-interpreter. So sysremote exec, the Python function that we added, only targets threads in the main thread. If you're implementing your own thing in Rust or C++, you can target any sub-interpreter because part of the protocol is that you go from PyRuntime to the interpreters list, then you can select the one that you want, and then from the interpreter list, you can select a thread from that interpreter. So the protocol allows any sub-interpreter. The Python version allows only the main one. But in the future, obviously, this is something that we can allow. It's just that we didn't want to, like the problem now is like you are in the business of like, how do you select as an interpreter, right? So you pass the address, but like, how do you find that? Like the problem is that you don't know you don't know the other process. So like, you know that there are 4 sub-interpreters, but like, can you refer by ID? Like, you know, it's a bunch of questions that we didn't have answers at the time. Threads is easier because you can refer to the thread as the native thread, so the pthread ID or the whatever Windows uses. So that's easy, but the sub-interpreter, it was kind of flaky, so it was unclear how to do it. So right now we don't allow to say, I want this sub-interpreter, but the protocol allows to do that. Yeah.
And then one other question. So you opted to basically send over file paths. Mm-hmm. And this is also going to the sys audit hook.
Yep.
Would it not make a little bit more sense to actually have the audit hook be able to see the exact code that will be executed rather than a file path? Because you do have a timing issue here if you do actually want to use it for code rejection.
So there is hooks in both sides. So there is hooks in the sending side, there is hook in the receiving side. So what you will be called is like the audit hook with the file. The reason, by the way, we need the file is because if we have like the code living in the process, like someone that has arbitrary rights to the process can have arbitrary exec by just writing to this place. So we need to pass the file to the, we need to use a file, and then we need to pass the file to the audit hook. So the audit hook technically needs to open the file, inspect it, and then...
Why not read the file contents and then pass the file contents to the audit hook? And then you execute the same file contents, because then you know that nobody can change the file.
Well, because the audit hook can do that itself, no?
Yeah, but there's a timing issue, right? Like if I read the file in the audit hook, and I say like, oh, now the file is okay, but someone then manipulates the file underneath the hood before I go to the execution, then I can give one content to the audit hook. But
Oh,
then
I know what you mean. Actually, yes. So this is changed indeed. Like we do that as well. Like so we don't pass the contents to the audit hook. We first read it. We call the audit hook with the file, and then we pass the file. The contents to the executing function. There is also some other race. What was the race? There's another race. We can see the code that is right now running on 3.14 because there's 2 races with that, but yes. It has been suggested also like to have another audit hook, not only on send, but like before it's executed, like to have one and enter and exit and a bunch of things, but like the conclusion is that your audit hook can do basically whatever it wants. Like it could even change the permission of the file if it wants, right? But there is an inherent race that you cannot get rid of because you can set the bit and then remove the file in the middle, right? So you could technically be running code that nobody can see now. Or for instance, the script that is running can delete the file. So if you then go, like, I don't know, the audit hook says something like Q or something, and then you go and try to read the file may not be there. Or maybe change permissions. But yeah, we can check it. That's a good question.
Okay, I have to interrupt you all. I'm sorry. I see your question. So if you want to, you can take it up and talk about it on the side. But we have officially run out of the time slot that has now been for your presentation. And thank you once again for your presentation.
Thank you very much.